Hello everyone, welcome to the last section of magnetism. In this video, we'll be showing magnetic field around a magnet, and these are the learning outcomes. We will first discuss how a compass can be used to determine the direction of magnetic field, and then we will learn how to draw magnetic field patterns around a bar magnet and between the poles of two bar magnets. And I have also included some uses of electromagnets in these videos as well. Okay, so before we start, you may pause the video to think about some of this question. I'm going to go through the answers now. Which of the following methods can be used to magnetize a bar made of a magnetic material? Okay, the answer will be C, because for A, B, and D, those are methods of demagnetization, heating it, or placing it in a solenoid with an alternating current will actually cause it to demagnetize if I were to remove the bar magnet slowly from the solenoid. Okay, in order to magnetize, I need to use a direct current, not an alternating current. So the best answer is by stroking it several times with a permanent magnet. So the answer is C. Next question. A metal rod is a permanent magnet if it repels another magnet. The answer is true because only magnets will repel another magnet. Okay, so repulsion is a test for magnetism. Next, okay, we can't really see magnetic field. So in physics, we usually draw magnetic field lines that is the visual tools to represent magnetic field. Okay, so over here, there are some characteristics of magnetic field lines. Number one, the magnetic field lines will never cross one another. So when you're drawing your magnetic field lines, make sure that they do not intersect with one another. Next, magnetic field lines are continuous and they form a closed loop. Okay, very often we just draw magnetic field lines coming out of a magnet. We don't really draw the magnetic field lines inside or within the magnet, but actually there are magnetic field lines within the magnet. And within the magnet, the direction will be from South Pole to North Pole. So when we draw it, it's always like outside of the magnet, away from the North Pole, and then towards the South Pole, outside of the magnet. But it continues inside the magnet. The last point about magnetic field lines is that the distance represents the strength. The closer the field lines are to each other, it means that the stronger the magnetic field is. Okay, so over here you can take a look. We always say that magnetic field lines always point away from the north, as seen from here, and towards the south pole. Okay, away from north towards south. Okay, so like this is an example where we always draw the magnetic field lines outside of the magnet. Okay, but within the magnetic field lines actually continues. So it actually continues from South Pole to North Pole inside the magnet. So it's one whole loop. Okay, next one, you can see that when it is nearer to the poles, the magnetic field lines are all closer together. Okay, so it means that the magnetic field is stronger when it is nearer to the poles as compared to at other regions where it is further apart. Okay, the magnetic field lines are further apart, indicating that it's a weaker magnetic field. Okay, so for uniform magnetic field lines, the magnetic field lines will be, for uniform magnetic field lines will be parallel to each other. They'll be all equally spaced out. And this is a non-uniform magnetic field. So you have a stronger magnetic field over this region and a weaker magnetic field towards the right side. Okay, next, these are examples of magnetic field, which we represent it with magnetic field lines for unlike poles and like poles. Okay, so for unlike poles, there will be magnetic field between the two poles. Okay, there'll be a force of attraction between them. So you will draw the magnetic field lines. There will only be straight line in the center from a north pole to a south pole, and then the rest curved. Okay, it's very similar to an electric field line. But for your like poles will repel each other. Okay, so this is North Pole and North Pole. So the magnetic field lines will be pointing away from the North Pole. So you'll be seeing something like this. Okay, there is a region, because of this repulsion between these two magnets, there will be a region X, which is called the neutral point. at this region, you will see that there is no magnetic field line, which means that the magnetic field at that region is 0. Okay, anything that you place here will not be experiencing a magnetic field. Okay, so these are some examples of magnetic field lines. Okay, so you can take a look. Most of them are curved lines. Okay, this is unlike poles. Okay, so there is a neutral point over here and here between the two poles. And this is like poles. So there isn't much of a neutral point. The only neutral point is here, which is actually very weak. Okay, so how do we determine the magnetic field lines? Okay, we can determine the magnetic field lines using the following method. It's a must for you to be able to describe experiments to determine the magnetic field lines around a magnet using a compass. So the first step is I just place a compass at the center of a piece of paper. Okay, and then I start to place my compass at either one end, either the North Pole or the South Pole, up to you. So I place a compass at one end. Okay, I mark the North Pole and South Pole of the compass needle with N and S respectively. Then I were to remove the compass and shift it such that the South Pole of the compass is at the North Pole of the, is at the end marking, which is the North Pole of the previous compass. Okay, and then I make another marking for the North Pole. And so I reposition my needle, my compass again, such that the South Pole again is touching the North Pole, is touching the end of the previous compass needle. So by doing that, okay, we will continue to reposition this compass needle all the way until it reaches the other end of the magnet. And then we can draw a line to join all the points, all the north and south points. Okay, this line is actually the magnetic field line of the magnet. Okay, so you can take a look at this direction. So a compass can be used to determine the magnetic field line's direction because the compass will always point in the direction of the magnetic field line. So if my magnetic field line is in this way, the compass needle will be pointing in this way as well. So at the top part over here, the compass needle will be pointing to the right. And at the, if I were to put my compass needle over here, it will be pointing to the left. Okay. Okay, so you need to know the definition of a magnetic field. So a magnetic field is defined as a region whereby a magnetic material experiences a magnetic force. So just a very quick recap, we have learned about an electric field, a gravitational field as well. So an electric field is a region where an electric charge experiences an electric force, while a gravitational field is a region where a mass experience a gravitational force. So for field, for definitions of field, is always a region whereby a something experience whatever kind of force. Okay, so that will help you memorize the definitions easier. Okay, so what happens when a paper clip is brought near to a magnet? It gets attracted to the magnet. Okay, why does it get attracted to a magnet? Because of induced magnetism. Why would there be induced magnetism? Because we say that the paper clip is in the magnetic field of the magnet. So the paper clip is a magnetic material. It will experience an attractive magnetic force, okay, caused by the magnetic field of the bar magnet. Okay, so it's as follows. You may scan the following QR code over here, these two, to see how the magnetic fields of magnets placed in different position looks like. So this is an example. If I have a North Pole over here, all my arrows will be going away from the North Pole, and this will be the direction that the compass needle will point in. Okay, which will correspond to the magnetic field line. The same for here, if I have a compass at A, it will point towards the right. If I have a compass at B, it will point in this direction, and C will point to the left, and D it will point to the left as well. Okay, so there is another thing that you need to understand is magnetic shielding. Okay, so what happens for magnetic shielding is I will make use of a magnetic material to protect or to shield something away from magnetic field. Okay, some of the equipments are very sensitive to magnetic effects, so they must be kept in some magnetic material to prevent them from reacting with the magnetic field outside, or to shield them away from the magnetic field outside. So you take a look at this diagram. I have a north pole and a south pole over here. So there is a magnetic field between these two opposite poles. Okay, so the magnetic field is represented by the green line. It's always away from the north pole towards the south pole. Okay, so what happens if I were to place a magnetic material in between this north pole and south pole? Okay, magnetic field lines would like to go through, or the magnetic field would like to go through magnetic material. So what you will see is, you will see that the field lines will all like to flow through this iron ring over here. Okay, so there will actually be no magnetic field in the center of the ring. Okay, we say that you can place your equipment here, it will experience no magnetic field. So this is mainly used to protect equipments that are very sensitive to magnetic field. Okay, and this entire process whereby I block magnetic field, or I block magnetic effect, okay, over an area is called magnetic shielding. Okay, next. You may pause the video to think about the answers. Okay, I'm going to go through the answers now. Can you draw the magnetic field between this pair of magnets? So you see a north pole and a north pole. You are supposed to draw a magnetic field between these two north poles. So it's a repulsion. Okay, so you will see a neutral point in the center, and it's a north pole. So you will see the arrows of the magnetic field lines are all going away from the north pole. So you will see something like this. Okay, so what is the direction that the compass needle will point? You will see that the magnetic fields are all going up here. So the direction that the compass needle will point, it will be upwards. Okay, next, you may pause the video here to think about the answers to the compass needle in the following cases. I'm going to go through now. Okay, so here is the north pole. You will know that the compass needle or the magnetic field will always be away from the north pole, so it will be pointing to the left. Okay, and then out over here is always away from north towards south, so this one will be right, and then this one will also be to the right. Oh, I do wrongly. Okay, this one should be to the right. Okay, north pole to south pole to the right. Okay, and then it will always be towards the south pole. Okay, next one, you should be able to see north pole to south pole, north pole to south pole, and then it will be always towards the south. Okay, the same for this, away from north pole towards the south pole and towards the south pole. Okay, next, look at these diagrams and the magnetic field lines around it determine the poles of the magnet. Okay, I'm going to go through now. So this one must be a north pole and this must be a south pole because magnetic field lines always go away from north towards south. This one, the arrows are all going away from it and there is a repulsion. So this must be a north pole, north pole. Okay, and this one is again a repulsion, but the arrows are going towards it. So it must be a south pole, south pole. Okay, then over here, I see the arrows is going down. So this side must be a north pole and this side must be a south pole. Okay, and similarly for this side, the arrow is going up, so it must be north to south. Okay, then next one, I see repulsion over here. Okay, so these two magnets must have the like poles. So this one, the arrows are all going away from the magnet. So this side must be north, this side must also be north, and this side is all arrows going towards the magnet. So this side, these two sides must be south pole. Okay, we move on to the last part already, which is some uses of electromagnet. We'll be zooming into three different applications of electromagnet, which is electric bell, circuit breaker, and simple magnetic relay. Okay, so for an electric bell, how does it work? Okay, so first step, when you press the bell button is pressed, you form a closed circuit. Okay, current will start to flow in this circuit. Okay, these red wires as can be seen. Okay, and then when current starts to flow, the first step, you always look for where is the solenoid. Because when current starts to flow, the solenoid will become an electromagnet. So current flows through this solenoid, this whole thing will become an electromagnet. And when it becomes an electromagnet, it will tend to attract some magnetic material. So over here, it will attract this soft iron armature. This iron bar over here is called a soft iron armature. So when it attracts, okay, this soft iron armature is attached to a hammer. So the hammer will move forward and hit the gong. Okay, but when the hammer move forward and hit the gong, okay, there is this contact point. Okay, so when you move forward, this contact point between this screw and the iron bar or iron armature is broken. Once this contact point is broken, we have an open circuit and current will stop flowing. So once the current stops flowing, electromagnet will lose its magnetism. So this spring or this iron bar will go back to its original position because there's a spring here that will push it back to its original position. And when it goes back to its original position, it will again close the contact. Okay, it will again close the contact over here and current will start to flow again, and then the hammer will continue to hit the gong again. So when you hear an electric bell, it's like ling, the bell rings non-stop. Okay, so the cycle keeps repeating itself. Okay, next for circuit breaker, how does it works? Okay, under normal condition, okay, nothing will happen. Okay, but whenever there is a large enough current, okay, a current that exceeds its rating, okay, that flows through this circuit, okay, this electromagnet will be strongly magnetized. Okay, if the current is not large enough, it doesn't exceed the current rating of the circuit breaker, then this current will still flow through. This iron bar will still be an electromagnet, but this electromagnet will not be strong enough to attract this soft iron armature. So when the current is large enough, okay, I produce a very, very strong electromagnet, I will be able to attract this iron armature. When I attract this iron armature, I actually break the contact over here. Okay, so this soft iron armature move forward and then the contact will be broken. Okay, and so the circuit breaker so-called trip. Okay, so in order to reset it, okay, we will need to press this reset button. Okay, this reset button with a spring, press it to push this iron armature back to its original position so as to close the contact for the circuit. This is how a circuit breaker works. Next, magnetic relay. Okay, so for your magnetic relay, again, current will flow in one circuit. So the current will flow in the first circuit through a solenoid, and this solenoid will become a very strong electromagnet. Okay, once it becomes an electromagnet, it will attract this iron armature. So when it attracts this iron armature, the iron armature is pivoted over here. So the top part of this iron armature will move up. And when it moves up, it will close the contact for the second circuit. So this is how a magnetic relay works. Okay, so let's answer a few questions now. You have 4 metal bars are placed in turn inside a coil of copper wire. The table gives the results of the experiment. So which rod would be most suitable for the use as a core of a coil in a circuit breaker? So you know for circuit breakers, I need to have an electromagnet in order for it to work. And the best material for an electromagnet is actually soft iron, which will make a temporary magnet. So in order for soft iron, for a temporary magnet, okay, soft iron has the characteristics of being easily magnetized. So whenever there's a current flowing through, I should have a large number of paper clips flowing through. So it should be C or D. I will be able to pick up a large number of paper clip. But once when I have my current switch off, okay, the soft iron should have lose its magnetism easily. So I will have very little paper clips attracted. So it cannot be D, it must be C, where I have very little paper clips still attracted to it. Okay, next over here, I have a diagram of a circuit breaker. Okay, you need to write the number that corresponds to each of the description. You may pause the video to think about the answers. I'm going to go through the answers now. So in the first step, okay, you will see that the contact is being closed so the first one will be because when a normal current flows through this solenoid magnetic effect will not be strong enough to attract this iron lever up, okay, or lever up. Okay, so when it's not strong enough to attract this iron lever up, this iron lever will keep this contact in place. Okay, so the circuit will still work. Okay, but then second picture, you see number 2 is over here, the iron lever is attracted up. So it corresponds to this. So when a large current flows through it, the solenoid will be strongly magnetized. And now because it's such a strong electromagnet, it is able to attract the iron lever upwards. Okay, and then number 3, you will see that the contact is broken. Okay, so once it attracts upwards, you have a spring over here. This spring will pull the contact apart. Okay, the spring will pull the metal to the right, separating the contacts. The circuit will now be open and no current flow. And then next, we'll go the spring. So it's this one. The spring will keep the contacts open. Okay, number 5 is this reset button, this yellow bar over here. After the fault is repaired, the circuit can be closed by pressing the reset button to connect the circuit, to connect the contacts again. So when I press this, I'm going to push this contact point close. Okay, I'm going to push number 3 to close up. So current can flow in the circuit again. So that's why it's called a reset button. Okay, so over here is a video of magnetic shielding. Okay, so what happens over here, you can see that the paper clip will no longer get attracted to a magnet when the new Singapore coin is placed between them, because the new Singapore coin is actually made of nickel, which is a magnetic material. So the magnetic field would like to pass through the magnetic material, which is the nickel coin. Okay, so it will not pass through to reach the paper clip. The paper clip will not experience any magnetic field, and therefore it will not become an induced magnet, and the paper clip will drop down. Okay, you can take a look. So the paper clip currently is being induced, okay, with opposite poles, so the paper clip gets attracted to the magnet. So when I place different materials in between them, okay, you will see that there is no effect because these are not magnetic materials. Okay, but now over here, I'm going to show you what happens if I place a magnetic material steel. Okay, you will see that the steel will get attracted to the magnet, and the paper clip will drop down because the steel will go through the steel. Okay, so this is the old Singapore coin. It's made of copper nickel. So copper and nickel are non-magnetic, and then this one is made of nickel only. Okay, so it's magnetic. So what happens is it will provide magnetic shielding. So all the magnetic lines or magnetic field will go through the coin instead of reaching to the paper clip. So the paper clip will not become an induced magnet because it's not under the influence of the magnetic field. Okay, so the paper clip will drop down. Okay, that's it.